Okay, let's unpack this. You might think we have, pretty good handle on our cosmic neighborhood, especially our own Milky Way galaxy. But what if?
Yeah.
What if our galactic home is actually surrounded by like way more companions than we've ever actually seen? Get ready for a deep dive today that it could completely reshape how we view the universe.
Absolutely. We're talking about this really groundbreaking research coming out of Durham University, and it suggests the Milky Way could be surrounded by maybe up to 100 satellite galaxies we've just never detected before.
100. That's huge. And these aren't just, regular faint galaxies.
No, not exactly. They're incredibly faint, very elusive objects. The researchers are calling them orphan galaxies.
Orphan galaxies. Okay, tell me more about that. How does a galaxy get orphaned?
Well, it's kind of a brutal cosmic process, actually. Imagine a smaller galaxy.
Right.
It gets drawn in too close to the Milky Way. Our galaxy's gravity is just immense. It basically strips away almost all of the smaller galaxies' dark matter halo.
Strips it away, like
Right.
completely.
Almost completely. It's like a cosmic wind just tearing away the invisible scaffolding. So what's left is this faint core of stars, almost a ghost,
Yeah.
That's why they're predicted to be nearly invisible to our current telescopes. They've lost most of the dark matter that would normally make them, well, more massive and easier to spot gravitationally.
Wow. So our own galaxy is kind of sculpting its surroundings, making these things harder to see.
In a way, yes. And here's where it gets really interesting, this potential discovery. It offers really strong evidence for the Lambda Cold Dark Matter theory, LCDM.
Ah, right. The LCDM model. That's the main theory we use for how the universe is structured on large scales, how galaxies form, isn't it?
Exactly. It's the leading model. And for a long, long time, LCDM predicted that we should see many more satellite galaxies around the Milky Way than we actually did.
The missing satellites problem. I remember reading about that. It was a big puzzle.
It was a huge puzzle, a real challenge to the theory. If the model was right, where were all these galaxies?
So this Durham research, it basically says, hey, they are here. They're just orphans.
Precisely. It provides this really powerful potential solution. It suggests they exist, but they've been stripped down so much by the Milky Way's gravity that they fell below our previous detection limits. So they were missing because they became nearly invisible ghosts.
That makes a lot of sense. It elegantly explains the discrepancy without throwing out the whole LCDM model.
It really does. It fits the picture of galaxy formation and evolution within this vast cosmic web that LCDM describes.
Okay, so how did the Durham team figure this out? If these things are so hard to see, how did they find evidence for them? So, like, the methodology must have been key.
Oh, absolutely. The method was the real game changer here. They combined two incredibly powerful tools. First, they used what's called the Aquarius AL1 simulation.
Aquarius AL1.
Yeah. Think of it as the highest resolution simulation ever performed of a Milky Way mass dark matter halo. Just unbelievably detailed. It maps out the invisible dark matter structure around a galaxy like ours down to incredibly fine scales.
Okay, so that gives you the dark matter scaffolding, as you called it. But dark matter doesn't shine, right? How do you get to the stars, the visible part?
Exactly. That's the crucial next step. And that's where the second tool comes in, the GeoForm model. GeoForm is like this sophisticated physics engine. It simulates how actual stars and galaxies would form and evolve within that dark matter framework predicted by Aquarius.
Ah, I see. So Aquarius provides the dark matter map, and GeoForm populates it with stars and galaxies based on physics.
You got it. See, earlier simulations could show the dark matter clumps where satellites should be, but they often struggled to predict if enough stars would actually survive the stripping process to remain detectable, even theoretically. GeoForm was advanced enough to track that. It showed that even these heavily stripped orphan galaxies should hold on to enough stars to potentially be seen.
So the models say they should have survived, even if earlier, less detailed simulations sometimes sort of lost them?
Right. The resolution and the physics modeling were key. They could track the abundance, the distribution, the properties of these orphans, and show they're a natural outcome in an LCDM universe.
Okay, so the theory and the simulations point strongly towards these 100 or so orphans being out there. What about actually finding them, seeing them with telescopes?
That's the next frontier. And honestly, our current telescopes are really pushed to their limits to see things this faint. We likely need new instruments. And the good news is, they're coming.
Like what?
Well, the big one everyone's excited about is the Vera C. Rubin Observatory. So physically, it's LSST camera. It's going to conduct this massive survey of the sky, deeper and wider than anything before. It's expected to have the sensitivity needed to finally detect these extremely faint objects, bringing them into view for the first time.
The Rubin Observatory.
Yeah.
Yeah, I've heard about that. It sounds like it could be revolutionary for exactly this kind of science.
It really could be. And interestingly, there are already some hints, maybe. Astronomers have found about 30 or so newly discovered objects. They're described as strange, tiny objects, very faint, very small.
Strange, tiny objects. Could they be these orphans?
That's the big question. It's possible. They could be a subset of this predicted faint population. But there's a debate going on right now. Are they truly dwarf galaxies, tiny stripped-down galaxies with maybe a little dark matter left? Or are they perhaps extremely faint globular clusters?
Okay, remind me what's the key difference there. Dwarf galaxy versus globular cluster.
It mainly comes down to dark matter and formation. The dwarf galaxy, even a tiny one, is generally thought to have formed within its own dark matter halo, even if most of that halo got stripped later. It's fundamentally its own galactic system. A globular cluster, on the other hand, is a very dense, ancient collection of stars that formed within a larger galaxy, like the Milky Way. It doesn't typically have its own significant dark matter halo.
So it's about whether they have that dark matter signature, however faint, and their origin story.
Pretty much. Astronomers are looking for subtle clues, maybe how the stars are moving within them, their chemical composition, things like that, subtle gravitational effects, trying to figure out if these 30 objects are true orphan galaxies or something else entirely.
Yeah.
It's a really active area of research.
It's fascinating. This whole deep dive, it really shows how we're pushing the limits, isn't it? It's not just about finding more dots in the sky.
Not at all. It's about testing fundamental theories.
Yeah, using physics and math, these incredible simulations, to make predictions, and then building new tools like Rubin to go out and actually test them.
Exactly. And we connect this back to the big picture. I mean, just thinking about potentially up to 100 of these orphan galaxies quietly orbiting us.
Yeah.
It's kind of astounding.
It really is. It makes the space around us seem much richer, more complex than we thought.
Definitely richer.
Yeah.
And crucially, it offers this powerful validation for that Lambda Cold Dark Matter theory, which, as we said, is really the cornerstone of modern cosmology. Finding these missing pieces would be a huge confirmation.
The prospect of finally seeing these missing companions with new telescopes, that's got to be incredibly exciting for astronomers.
Oh, absolutely. It could tell us so much more about how our corner of the universe, how the Milky Way and its neighbors actually formed and evolved.
Yeah, it's like discovering your house has all these hidden attics and crawl spaces you never knew existed.
That's a great analogy. It really makes you reconsider what's out there in the empty space. And maybe this raises a question for you, listening right now. What else might be hiding in plain sight? Not just in space, but maybe in any complex system. Are there other fundamental ideas, maybe in science, maybe elsewhere, that are just waiting for the right tools, or maybe just the right way of looking at the data to be revealed?
Yeah.
Yeah.
What faint signals are we missing right now, just beyond the edge of what we can currently perceive?
It's a compelling thought.
It really is. It's a powerful reminder, I think, that discovery isn't always about, boldly going into the completely unknown. Sometimes it's about looking much, much closer at what's already around us and finally understanding its true hidden significance.